Let's begin with why numbers exist. We'll start from a need to count. If you have some number of flying squirrels, you need some way to measure how many you have. That's what the characters of numbers are used to represent. But when you get larger amounts, you can't keep making more and more characters. Because of that, we group them into digits. Instead of making more characters, we create a base system in order to count larger numbers. And since we have 10 fingers, we have base 10. 10 isn't the only base though, and many others are and have been used throughout history. While there is more interesting math to explore in bases, that's a different story. Back to our story today, the squirrels could be in different groups. And if we know how many are in the first group and how many are in the second, we can see why addition would be useful. Instead of needing to go back and count them all over again, we can simply use addition to skip the recounting. Likewise, if we counted the total in only one of the groups, we can use subtraction to know how many are in the other. This is nice, but where we can get more power from counting is when you have many groups, but each group has the same number of squirrels. Now we get multiplication. Again, division is the opposite because you can use the total and number of groups to figure out how many are in each group. Alright, that's a simple, quick, and hopefully straightforward run through of arithmetic. But get ready, because we're going to move into the more complicated part of the story. Let's suppose there's a group of 3 flying squirrels that are lining up to buy ice cream. If there are 4 available flavors, how many ways can they pick flavors? Well, they each have 4 choices, so 4 for the first times 4 for the second times 4 for the last is 4 cubed, or 4 to the third power. Here we are introduced to repeated multiplication, or powers. They're pretty helpful, but aren't going to be that important to this story. Okay, so back to the story. What if they want different flavors? Well, the first still has 4 choices, but the second can't pick the same flavor, so there are only 3 remaining. And the last squirrel only has 2. Instead of 4 cubed, we have 4 times 3 times 2. Now the reason we can do this is no matter what ice cream is taken by the first squirrel, the others still get the same number of choices. Now that we've looked at their choices to buy ice cream, how many ways can they line up? In this case, there are 6 ways, the ones you can see here on screen. But to get to that conclusion, there's a better way than just trial and error. There's actually a mathematical way to solve the problem. We can go through the spots in line to see. Any of the 3 can be first in line, any of the other 2 can be second, and the remaining one will have to be last. A good way to visualize this would be by making a tree diagram. First, you have 3 options for first in line, each of them then has 2 more options for second in line, and the remaining flying squirrel has to be last. With this, we are introduced to the factorial function, where you multiply numbers down from your number. But let's go back a bit. This way of counting is actually really important. We can multiply because each factor stays the same regardless of what happened before it. Regardless of which squirrel or ice cream flavor is picked first, there's 1 less option for the second and 2 less for the third. Consistency is key because if it wasn't consistent, we wouldn't be able to use multiplication. Alright, now let's suppose there are 4 squirrels, but they realize they can only buy 2 ice creams. They decide to pair up and split an ice cream each. How many ways can they pair up? A way to approach this problem is first looking at how many ways you would have a group of 1. This is simpler than it sounds because it's just 4, the number of squirrels. Okay, so there are 4 possible groups of 1, and in each scenario they can be paired with one of 3 squirrels. While that would make 4 times 3 equals 12, you actually overcount. You could pick squirrel A and then B, or B then A. Both cases would be counted in the tree diagram. In this case, we would divide by 2, but in a more general case, we would divide by the number of ways they can be ordered, because that's how many times each case would be counted. So how do we do that? Well, by using factorials. For those who don't remember, factorials just multiply down from the number. So like 5 factorial is 5 times 4 times 3 times 2 times 1. Using factorials, we can see that what we got previously is actually 4 factorial divided by 2 factorial 2 factorial. The general formula is n factorial over n minus k factorial for k things picked. We would call this the combination function, or in a more specific case, n choose k. So back in our case, we have 4 squirrels, and we choose 2 of them, so we set it up as 4 factorial over 4 minus 2 factorial 2 factorial. By the way, we did pass permutations, which is just taking 2 of them in order, which would be 4 times 3, or 4 factorial over 2 factorial. This would be like the ice cream flavor example, where we had 4 times 3 times 2, which is 4 factorial over 1 factorial. Personally, I don't like permutations as much, so we'll just ignore them today. Their notation is the p, which can be similarly used for combinations, but with the c. Now, the combination function is actually pretty nice because we can now catch multiple animals. Let's say we add some deer to the mix. Now, instead of caring about each individual animal, we only care about their type. So let's say there are 3 flying squirrels and 2 deer. To figure out how many ways they can line up, we can just use the combinations. We can think of this problem in a different way, where the animals are lined up, but we need to pick 2 of them to be deer. This way we get 5 choose 2. However, the problem can also be approached as picking 3 of the animals to be flying squirrels. Nicely, they reach the same conclusion, because 1k is the other's n minus k. 5 choose 2 equals 5 choose 3. Pretty nice, right? Alright, as the last part of the story, let's just go back to having 4 squirrels. Suppose they now want to share 7 candies among themselves. How many ways can they distribute the candy if every squirrel gets at least 1? So the first thing we can do is give each squirrel 1 candy. There are then 3 left. Now to actually count them, we're going to use an interesting method. Instead of thinking of this problem as a problem with 4 squirrels, we'll just say we need to divide the candies into 4 groups. The 4 groups need 3 dividers, and we have 3 dividers and 3 candies. All that's left is picking the 3 dividers among the 6. Therefore, the number of ways to distribute our candies is 6 choose 3. Now the reason we need this workaround is because the candies aren't distinguishable, but the squirrels are. Only where the candies end up matter, not which candy goes where. That's why we can't just say it's 4 times 4 times 4. On the other hand, the order of the squirrels matter because that's how we distinguish them from one another. This method of counting is commonly called balls and urns or stars and bars. There are more names, but these are the more common two. And unfortunately, that's where I'll end today. Everyone has candy, and we can call this a happy ending. I hope you enjoyed this video and found the presentation fun. I'll probably try to delve deeper into other math topics, so I'll see you next time. Goodbye!